Hi, I'm Bob Sorensen. I'm a chief analyst for quantum computing here at Hyperion Research. And today I'm going to give you a fast and furious tour of what's going on in the quantum computing sector, specifically how it's finding its place in the overall advanced computing sector. If there's one takeaway that I'd like everyone to have from today's little discussion, is that quantum computing is not a standalone technology. It's not something that here's classical computing over here on one island, and here's quantum computing on another island. Quantum computing is more about another tool in the toolkit for advanced computing. Think of it in some sense as a version of a GPU in the sense that quantum computing offers some significant performance advantage for a key but narrow set of applications that ultimately complements the overall advanced computing architecture, but certainly will not supplant it, will not replace it. And that's probably one of the biggest takeaways that I hope we get out of this discussion today. So let's just jump right in here. If you've been reading the paper or the technical journals for the last few years, you understand that the promise of quantum computing is substantial. The idea of using quantum physics phenomena such as superposition and entanglement and operating in the quantum space versus the classical binary digital space offers some very substantial performance gains. And increasingly, those performance gains are available in a wide range of applications. Some of the ones that are receiving the most attention today are the areas of physical simulation in areas like material science, chemistry, the pharmaceutical sector, and certainly in oil and gas. There's some interesting work going on in quantum accelerated machine learning capabilities to really help augment what we see going on in the classical world of machine learning, deep learning, and other variants of artificial intelligence. One of the ones that I think right now is one of the most popular is the optimization opportunities in quantum, the ability to take existing algorithms or existing objective functions to optimize a process, turn it over into the quantum realm, and figure out better ways to maximize an outcome, for an example, figure out the best way to load a large group of luggage and other materials into the cargo hold of an Airbus airplane as it turns around as a gate. What's the best way to get it the most luggage in there in the least amount of time? Those kinds of optimization problems are one that's really driving a lot of the interest in quantum computing today. And as I stress, that list grows longer each day. There's lots and lots of innovation out in the field, people looking for new ways to adopt what we know about quantum computing from a technical capabilities perspective and grow that list of applications. Now, ultimately, the goal of all this is to demonstrate what they call quantum supremacy. And that's using a programmable quantum device to solve a problem that no classical computer can solve in any feasible amount of time. And the example there that people talk about is an algorithm invented by Shor while he was at AT&T, appropriately called Shor's algorithm, which does something actually wonderful. It's able to factor a large number into its two prime integers. Now, to the uninitiated, that may not sound like a very interesting problem, but the fact that that is one of the underlying mathematical principles that ensures the security of a large percentage of data encryption and protection schemes that are available today has given that particular algorithm a certain amount of interest at almost every level of research, simply because it is pervasive in so many different applications today. And the key there is that the Shor's algorithm can do something in, say, a few hours in a theoretical classical computer, or excuse me, theoretical quantum computer that may be available perhaps in a decade or more. That would take the age of the universe to compute on a classical counterpart, even at the highest levels of performance. So that's the high point of all that. But ultimately, we'll get to this. The reality of what quantum is today, and will probably be for the next few years, is quite frankly much more realistic. And we'll discuss that a little bit going forward. Well, I talked a little bit about quantum computing based on quantum phenomena such as superposition and entanglement. And right now there are many quantum modalities, the different ways that researchers can achieve the desired quantum phenomena to basically field qubits, quantum digits, if you will, the counterpart to binary digits or bits. And we call those different quantum modalities. And right now there's a whole bunch of different considerations being looked at today. Superconducting qubits, photonic trapped ions, spin quantum dots, NV centers, diamonds, topological, adiabatic. This horrible eye chart on the left, the inner red circles gives you the different modalities, and the outer circumference of the circle, gives you all the organizations right now that are researching those different modalities. So what this chart says, even though you can't read it in this format, is that there are many ways to basically support the quantum phenomena for quantum computing, but there is no clear winner as of yet. Each of these offers specific particular strengths and weaknesses in terms of the fidelity of the qubits, how many can be packed perhaps on a single processor, their ability to scale to larger qubit counts, all sorts of different factors that would make the ultimate perfectly scalable qubit to result in, say, a quantum computer in the future that has 1 million qubits on a processor. But right now, each of them offers their own strengths and weaknesses. And at this particular point in time, there is no clear winner. And what I like to say, perhaps somewhat provocatively, is perhaps if we could move the clock forward, say 15 years, the quantum modality of choice may not yet be on this list. So by no means is the race over. By no means has a winner been declared. This kind of leads into the sense that really there are significant challenges ahead to the realization of quantum computing becoming a mainstream and somewhat ho-hum technology. There are formidable technical issues in quantum computing hardware and software. The performance gains right now are uncertain. It's difficult right now to have demonstrated use case performance to say, here is an existing quantum algorithm that runs on an existing quantum system that gives me a performance advantage of X over a classical counterpart. We're still trying to deal with, I don't want to call them toy problems, but essentially proof of concept problems in quantum computing that hopefully will lead to significant performance gains down the road, but we still haven't reached demonstrated use case capability in basically undeniable terms. The timeframes are unpredictable at this point. The sector makes advances in leaps and bounds, or then it can sit still for a little bit of while. I like to say whenever I see technology development charts that chart the progress of some quantum computing capability, that the time scale on the x-axis is nonlinear. And it doesn't move in any predictable way. You can have lots of pockets of acceleration with some real troughs of development and such. So that the performance gains, the time frames are somewhat arbitrary right now and not very predictable, as we've come to expect in terms of kind of the Moore's law progression in classical computing. Workforce issues are an interesting problem here. There's lots of esoteric physics and other related hardware and software and engineering concerns in fielding a quantum system, and the pool of people who can deal with those issues is somewhat narrow at this particular point in time. If the technology takes off in the way that a lot of people think it will, it's not going to be easy to go out and find the kind of skilled workforce you need, either from the university system or from retraining existing advanced computing professionals. So there is some concern in the next few years that there may be some workforce issues and that certain vacancies may go unfulfilled for an awful long time. Well, all of these factors, they really complicate treating quantum computing as a stable market alongside more traditional IT sectors. And for many, including the corporate world and the investment community, that means that making the business case is tough, but something needs to be done. There needs to be some sense of predictability in the market, a way to perhaps not think about where the market's going, but at least a better way to understand and assess the risks involved in investing in this particular technology. And so really what we're seeing now within the sector is this sense of how can we assess the risk, assign a value to it, and continue to receive the fundings and provide the development opportunities so we can turn quantum computing into a sector that has a virtuous cycle. R&D generates products, products generate revenue, revenue support R&D, and so on. And that's really, I think, one of the next imperatives for the sector, say, in the next few years. Well, I just want to give you a quick overview of what's going on from our quantum computing research perspective from 50,000 meters, just to give you a sense and really drive home the point that quantum computing is not a technology or an activity that is centered in one particular geographic location or is owned by one particular IT organization or series of organizations. This is not an extension of legacy IT. This is not something that the US owns by default based on 40 years of IT leadership. This is not something that companies that have been involved in classical IT or even organizations or countries that have been involved in classical IT have any kind of leg up. It's a greenfield technology, and it makes for some very interesting implications going forward. I'll get into that in a little bit. Well, this is just a quick chart that shows national level quantum computing research publication volume by nation between 2016 and 2020. And on the right here, you see I did a very simple query, and I did this about 2 months ago, and I ended up receiving about hits on about 17,000 high-quality R&D publications in the last 5 years, and have sorted them by country. And the quick takeaways from this is, there's a few. The first one is that the United States and China are really neck and neck when it comes to published research in quantum computing. I don't think that would surprise anyone. But to me, what I find interesting is the number of other countries in the world that are posting reasonable amounts of research activity in these publications. And you can see that Germany, UK, India, Canada, and this list goes way down all the way across. If I had more room, I could show you. This is an international phenomenon. This is, as I said earlier, is not owned by one company or one organization or one country. It is a global phenomena. The other thing I'd like to point out here is you'll notice that as time progresses between 2016 and 2020, the general trend is towards more research. It's fascinating for me to see that not only are many countries doing this, but all of them, almost all of them, are on a serious upswing when it comes to doing research in the activity. So the point here, global phenomena, not something that's owned. The decisions haven't been made on who the winners and losers are, and there's an awful lot of activity. And a lot of it is coming from countries that I like to say are punching above its weight in their traditional positioning in terms of classical IT. So you see countries like India and Canada and the UK, not exactly IT powerhouses, but are playing quite aggressively to get involved early on in the quantum computing sector. This is another favorite chart of mine because what all I did was I took the derivative with respect to leading organizations on the previous chart and just put out the number of publications per organization. It should come to no surprise that, the Chinese Academy of Science and USTC of China are two of the leading organizations. But if you look at this list, you'll see that there are 6 different nations represented in the top 10 list here. And I should note that the interesting thing is the reason the Chinese academies show up at the top is because they're responsible for the preponderance of what's going on in China. This is, if you want to know what's going on in China, you basically look at these two organizations as kind of a harbinger of what the rest of the nation is doing. Whereas in the US, which had about the same number of R&D publications, it's a much broader base of more research facilities, universities, government research facilities, but spread out over a larger base. So it's really a difference between a small number of groups in China doing a lot of work and a much larger number of organizations in the US, each of them doing work, but doing it to a lesser degree than what's going on in China on a per institution basis. Key here, though, six out of the top 10 nations represented here. I find that to be an interesting activity. One of the reasons that this is happening is because we're seeing a plethora of select national, regional government promotion programs in quantum computing. And this is a list of just some of the countries that are involved in what's going on in terms of funding quantum computing research at the government level. And first off, again, the global perspective here, lots and lots of countries involved. These are all considered to be, in my mind, major programs approaching $1 billion a year in funding in some organizations. But the key here is that this is not an exhaustive list per country. Some of these are only a representative sampling of what's going on within a particular country. So it doesn't mean that Japan is only looking at one particular quantum government promotion policy. It means that this is the one that I thought was the coolest at the time I was putting together this slide. So the key here is lots of governments and lots of programs within those governments. So it is definitely something that the governments around the world are funding with a great degree of enthusiasm. This is something that we're seeing much more and more of going forward within the sector, which is that end users are increasingly weighing in. End users are anticipating quantum computing. They're trying to figure out how to bring it into their overall workspace, and they are very interested in establishing the capability to sit at the table and say, this is what we're interested in. And the way that they're achieving this in the first order is partnerships with individual quantum computing companies. But what we're seeing more and more now are non-competitive collaborative efforts going on around the world. We have the Quantum Economic Development Consortium in the US, funded out of the US government, but still it's a very free-flowing, open organization to foster the competitive aspects of quantum computing. We're seeing the same things with the Quantum Industry Consortium in Europe, where we have a mix of QC suppliers and major industrial players. Japan, under the initiation of NTT, one of their larger telecommunications firms, just organized a cooperative organization of 11 leading Japanese industrial players. We saw the same thing in the last few months in Germany with 10 industrial players, automakers, advanced manufacturing, investment houses are involved in saying, we want to at least be involved in thinking about how use cases can drive what we see in terms of quantum computing offering from the suppliers. So in some sense, we see what's going on in the quantum computing sector in terms of push. Now we're seeing pull, what the end users are interested in. I'm just going to give you a very quick overview of what's going on in the commercial landscape. A number of growing and diverse players. The kinds of folks you'd expect to see: IBM, Atos, Fujitsu, perennial IT suppliers who are looking at quantum as an alternate supplier of or a way to augment their existing advanced computing portfolio. We see integrated players like Honeywell who are trying to actually build quantum in some sense to support their own vertical product lines, or excuse me, horizontal product lines. A whole host of new entrants in terms of pure play quantum makers: IonQ, Rigetti, Cold Quantum, Quantum Circuit, Xanadu, IQM. Venture capital funding, government funding activities. The key there is they are looking to drive revenue. They are looking to really put a stake down in terms of driving the sector. We see a bunch of non-traditional players here, which is kind of interesting. I just put down 5 here, not taken at random: Alibaba, AWS, Baidu, Google, and Microsoft. And we'll get to that in a minute. And also we see myriad stealth players, lots of small companies around the world, got some VC funding and are interested in trying to find where they can make their way into the quantum computing ecosystem. I mentioned those companies, the 5 non-traditional players. I picked 3 of them because all 5 of them are cloud service providers. 3 of them are 3 of the largest cloud service providers in the US. All of them are banking in quantum computing, not only by offering cloud access models for existing hardware suppliers, but doing applications development, doing their own quantum computing hardware. It's a really interesting play for these cloud service providers to be looking at some of their first real indigenous hardware and software R&D capabilities, throwing money back at quantum computing as what they consider to be, I think, a differentiator and a way to make their particular cloud service products unique, based, compared to their counterparts. And that's an interesting development in and of itself. I put this, again, another horrible eye chart here, just to basically show the fact that there are a myriad software companies out there who are trying to find their place in the quantum computing ecosystem, whether it be for quantum compilers, quantum applications, or even quantum services, if you will, targeted towards specific verticals. The reason I put this chart up here is not to stress your bandwidth in terms of high resolution display, but to basically show that because the sector is somewhat coalescing into a organized hardware software stack, software companies can now offer products that are usable on a number of different modalities. Remember, I mentioned earlier that hardware modalities are varied. There's lots of opportunities out there. No one knows who's going to win. But what's happened happily within the software world is organizations can write software that can run on different hardware vendors. So these software suppliers don't have to pick a single modality or vendor. They can sit at a level in the software stack that says, I can write a usable application that can run on a D-Wave system, that can run on Honeywell or whatever. It's an interesting phenomena here from the software perspective. I just want to give you a quick sense of market dynamics. We did a study last year for the Quantum Economic Development Council. If you're interested, drop me a note and we can send you some of the results. The bottom line is we after some exhaustive surveys of both quantum computing suppliers and end users, we came up with some numbers. Quantum computing market worth about $320 million in 2020. That's the global market. And we're looking at about a 27% CAGR for the next 3 to 4 years out. And we have some more details there. But really, the point of this exercise was to really say quantum computing is a market. We can basically say there will be some growth here because we got commitment from end users in terms of budgetary commitments over the next few years. There is some stability to the market. There is a way to size it. And it's something that we're continually working on. Remember, in the very beginning, I talked about realistic. What are users thinking about in terms of what quantum can bring versus this idea of quantum supremacy, intractable on a classical counterpart? Well, we asked a bunch of quantum computing users what performance that they would need to see on existing workloads to say, hey, I'm ready to go and write a check and bring quantum computing into my advanced computing capability. And what we found, and that one of the bullets on the right there, was about 42%, almost half of the users we surveyed, said as long as I can get 50x or below, and 20% said they'd only need 10x in order of magnitude to really think about bringing quantum computing into their environment. And I find this to be a very satisfying result because it means that while some of us are more or less, I don't want to say fixated, but at least perhaps overemphasizing the quantum supremacy and some of the incredible speed ups that quantum can bring in the near or perhaps even distant future, the user base is saying, all I need is a 4 to 5 year boost over my competitors based on what I would see in the classical world. You give me 50x performance improvement, that's really what you're going to get in the classical HPC world. You wait 5 years, you get 50x performance back. That's what the users are interested in right now. And I think that's an important point to make to the suppliers of the quantum sector, that the users are looking for competitive advantage and economic payoff in quantum. They're not looking for the very aggressive, far-reaching performance potentials of quantum. They just want to be able to work faster and smarter on their near-term jobs. How this really plays out near term is we're looking for growth in the market. We're looking for new applications, not only targeted for traditional HPC, but we're seeing more and more uptake in the enterprise IT computing sector, where they're saying, hey, there's some opportunities here, say perhaps in the optimization field, where we're not HPC users, but we could benefit from an accelerated capability in, say, optimizing a process. How do we lay out our factory? How do we move materials through an advanced manufacturing facility in an optimal way? One of the interesting things which makes the sector so amazing and confusing and interesting to watch is development is happening in many directions, and all of it in parallel. As I said, we're seeing different hardware, qubit modalities. People are thinking about interconnects. How do we, if we build 1,000 processor qubit, how can we configure that to make a 1,000,000 processor system if we connect 1,000 processors together, each processor with 1,000 qubits? So the idea of quantum computing LANs, quantum computing networks, how do we think about the overall architecture of QC to really start to field systems that can actually deliver some impressive performance in an industrial capability? We're seeing things like hybrid classical quantum systems, the idea of iterating between a quantum and classical computer to take advantages of the characteristics of both to reach a specific solution and application. Lots of interesting work there. Quantum-inspired hardware and software, the idea of looking at advances in quantum theory and quantum algorithm and saying, hey, some of that can be driven into existing classical algorithms to speed up performance. We're seeing lots of examples of that, and that's an interesting offshoot of quantum that I think offers much more potential than a lot of people are thinking about right now. And finally, I want to drive home again the point that I start out with. Quantum computing is not a replacement for classical computing, but simply, and I don't say simply lightly, but merely or exactly another tool in the advanced computational toolbox. And that's really, I think, one of the main takeaways that I wanted to get on this session today. That's the end of my talk there. If you have any questions, follow-ups, or just want to just chat a little bit more about this, here's my email address, and I hope you have I hope this session was worthwhile listening to, and I just want to thank everyone for their attention.